first of all, thank you everyone for coming, and so we had so nice practically finished workshop. And I'm not going to speak about any hard things, so I knew that my talk would be the last one, even it was postponed for half an hour. So I hope that it should not be too painful. And okay, let's go. So first of all, listening Leonid's talk that greater generality builds simplicity, understood as something not for me because it's too complicated. So I decided that would be simple cases, maybe in better understanding, with a hope to come a bit closer to the general case. So for that reason, I hope it would be much more simple than that. I allowed myself very fast to tell. Okay, to show where I'm coming from now. It's from Aberystwyth. It's another side of this island. It's a Wales. It's in the middle of the Cardigan Bay. It's middle Wales, middle of Cardigan Bay coast, and middle of nowhere because it's very difficult to reach the place. So it's a small town with 12,000 inhabitants, 12,000 students. The university, it's the first Welsh university appeared by mistake or accident, but anyway, we're very proud and happy about this. It's an old college. This is exactly first Welsh university. If you have nice weather, it looks like that, so it's really, you can enjoy this weather. We have even marine, so if you have your own boat to swim from somewhere else, you can use it. But then if the weather is not so good, then it may be looking quite different, so then you should postpone the visit for some time. But now let me move to the presentation itself. So it's something in the plan. As you can see, actually no series is here, and serious things would only come in here, but very short. So I'm really try to be very simple, and we'll need really your help when we are coming to the third point, because I try to understand myself what is going on with all these questions about partial indices, and to understand I need to play some very simple games. So this is simply a repetition many times. On this workshop we saw this result, so we know that we are dealing with some nice function, matrix function, should be non-singular, should be in some good nice space, and then the general result is like this. We can finally factorize this, at least theoretically, with the factors. What is very nice behave in the respective in this case domain. So in upper half plane or lower half plane, it's depending on what we are speaking about. Here I simply draw for simplicity the case on some finite smooth domain. So we have the so-called set of the partial indices. They are fortunately unique, at least this is unique, so we have some good result, and we can compute total index. So what we know really is, I'm trying to summarize what we know from the literature and from this workshop too, that the total index actually is stable with small perturbation of the initial matrix. So it's a very good news, so we can perturb the initial matrix and no problem with the total index. So what we know that if you perturb it, again, if the matrix remains with the same class, what I mentioned, non-singular and so on, then we again can factorize, and then we have again the partial indices, and here the first pain came, that the partial indices are only stable if and only if this nice properties is valid for the original one. So the difference between the maximum and the minimum partial indices is not more than 1. Okay, the same story could be said for the left-hand side. Everything was written in the right-hand side factorization. Okay, so then what does it mean? In fact, if you think about this somehow in abstract way, so it's our matrix function in the appropriate space. So we know that the original, the partial indices of this matrix function satisfy the stability condition. Then if we perturb this matrix in some, again, appropriate space, everything is nice. We know what is going on. and the partial indices would be preserved. So what happens if you are in an unfortunate situation where the partial indices are not do not satisfy that nice condition? So again, we are in some neighborhood of this our original matrix, but now we can find everything what we can. So we can find something what is stable, we can find something what is canonical, then all partial indices is even to 0, and we can find something what is exactly as we are here, and try simply to have a path, because this epsilon you can think as, because you can change this epsilon from the value and with a limit to 0, then this you have actually path in this neighborhood how you approach this point. So if you are happy to approach this point in a way that partial indices are not changing, so you are on a safe side. At least you know what is going on, and actually this is the main problem. Can we do something with approximation to stay in the situation what we know? Because what we assume that we know everything about this original matrix G0. So we know everything, we know how to factorize this, we know by chance that we know all the partial indices, what is additional problem, and we call this, I will call this 1 million problem by Ilya Spitkovsky. Okay, he's not even happy to listen about this.
Listening very carefully.
Okay. Okay.
Point out
Something. Okay, so the final summary. So if you are speaking about scalar, everything is nice, absolutely perfect, and nothing to be worried. Apart of the fact you should be very careful working with the poles, zeros, and so on, if they are around the line where you're factorizing. But when you are going to the matrices, then we have two red, very dangerous statements, what any of the applied mathematicians and engineers should not be very happy of, especially applied mathematicians, because probably engineer doesn't care at all about this. And then, okay, then the good news is that time to time, and there is a collection of this time to time when you can really factorize. So this, at least we could grab some G0 somewhere. If we would not be able to do even this, we are in a very bad situation. But we at least can grab somehow G0 here, G0 there, and try to think about the path, how to still survive in this unfortunate situation. And we also have a belief, what time to time also was mentioned here, that all practical problems always reduce to the canonical case. No problem to be worried about. If this belief would be reformulated in other ways, that any wise, experienced, and lucky scientist dealing with the Wiener-Hall problem, he will not have any problem, and he will definitely come to canonical factorization. So if such belief is formulated, I agree with this. But it requires at least, and the problem is good. So actually I forgot about some other. So it's very nice belief, but we should somehow check it. So now I would suggest the quiz, and I need your help and Nastya help. We will now try to vote. So the idea is we have unfortunate situation. We have small perturbation of the matrix with unstable set of partial indices, and I'm trying to do something really interesting. So I try to make this path in a way to preserve as many invariants of this original matrix as possible. Not only something like index, but the full value of the invariant. So the suggested answers are 3. Property would rather help, property would not help, and I do not want even to guess. So please, Nastya, try to collect the vote. Please, who is for the first statement? In the favor of the first statement.
Statement number 1.
Oh, just a second. Can you clarify what invariants are?
No, it's okay.
If invariants are partial indices, then it's definitely yes.
Okay, so no, invariants of the matrix as we understood them. I mean, determinant, then the next, and then something like invariant of the matrix as a matrix, So actually, I'm understanding invariants as a functions. So I'm preserving not only the scalar value, full functional, very strong prescriptive. Now it's easier to make a decision. Okay, Nastya, please.
A. Who votes for A? 1, 2, 3, 4, 5, 6. People undecided. B. 1, 2, 3, 4.
Okay.
C.
Okay. It's at an end of the workshop, so nobody wants to take a guess. Okay. So anyway, if you are in a exit poll situation, we would say that the first group would rather won in comparison with the second one. A bit. Of course, we have too many people not coming to vote at all. But anyway, it's something like this. So I will try to play with the famous Goldberg-Crane or Boyarsky example. It would be 2 by 2 matrices. Everyone could compute very easily, and this is absolutely trivial and nice stuff. This is what I've done. So we have the matrix like this. It's on a unit circle, so T is going around the unit circle, and the perturbation is like that. So we're preserving fully the first and the second invariant of this matrix. Absolutely the same as a function of T, not only like index or something like this. It's completely everything is preserved. So about this matrix, it's a famous internal matrix what appeared in diagonal matrix in the factorization. So we know from this that the partial indices are -1 and 1. This is for sure. So what is about this guy? So the example what was constructed by those famous mathematicians I just mentioned, you can see that result is that partial indices are zeros now, because this matrix is analytic inside this circle. Outside, actually, the determinant is 1. The determinant here is also 1. Okay, here we preserved everything, and we changed the partial indices. We didn't change the main. So those who vote for the first yes should become really worried now about. So then preserves all the invariants, and since even point-wise, it didn't help to stabilize the partial indices. Actually, it was counterproductive. The same story, it's the same exactly example. I put -2 and 2, taking the same example simply because I want to show to be in between. So I tried to play around again. So we're doing absolutely the same story. We have again very trivial factorization. You can check that this is really true. And again, so what I mentioned, that we came from the situation -2, 2 to 0. I forgot to mention previously something interesting happening here anyway, because in both of the factorization terms we have epsilon with a -1 degree. So when epsilon goes to 0, those two guys actually blow up. It's simply in one point the indices, partial indices -2, 2. As only we jump a bit, whatever epsilon, we have completely other situation, and moreover, as we are moving from this situation, it becomes better and better. Okay, so now I constructed another example, also very simple and easy. So after manipulating, so we added this term here and manipulated a bit, we're now having from a jump from -2, 2 to -1, 1. And absolutely the same story. Okay, try to make some other perturbation of the original matrix. It's absolutely trivial, so simply multiply this by the diagonal matrix again. Nothing preserves, and everything is perfect. So you're preserving your partial indices, no problem whatsoever. Actually, the left and the right matrices are simply constant because we are multiplied by the constant. So nice news. The same if you perturb here, okay, you again change the both invariants, and again you can construct nice factorization which is preserving everything what you wish to preserve. So as a result of our small quiz, we should say that those who vote for the first probably lost the chance to win a huge money. And so if we really preserve too much from the original matrix is not helpful. If you're not preserving this helps, looks like perfect, and I can give, I try to give some reasonable explanation for this, and the explanation was, okay, we want to construct a regular approximation, so we do not want to do anything with the partial indices, so these two guys from both sides should be good, should not blow up, and then we can do this. So we should construct this, but we simultaneously not allowed to construct this in any arbitrary way. We additionally put some additional construction condition for this. Of course, it's not easy. So this is an explanation like to find any such a sequence, we should really satisfy this factorization condition, and we better not to do any more than simply allowed to do this. But I have another example. So you see that majority won actually, because I was able to construct the example which is really destroyed the invariance and also push the indices to change. So there is no answer that it helps or not helps. It's we are somewhere in the middle, so nobody knows actually what is going on. Actually, the only answer from this is that if you're really sitting on the functional invariance of the matrix function, it's not helping to do approximate factorization. So you should know something more than that. You should be deeper in this. Okay, so okay, I can start playing that, okay, I did something what is anyway didn't change, but I don't want to play around because it's something. Oh. Okay, so come back to the story. So we know that partial index is stable in this and this, then perturbation is perfect. We know that if any regular perturbation of the original matrix would stay with the same partial indices, it's not a result, it's simply conclusions, and we know this. We know that better not to restrict. But the problem, what I'm telling not to restrict, actually what I mean that this G epsilon is what we have from our problem. We need to solve this. Actually, we don't have too much freedom on that. So we were given G epsilon, which is our problem, practical problem. It was constructed by the nature. So this means that now the question, can we find something anyway to check that we have regular factorization and how to do this? And so, as I just mentioned, it's not 1 million. Answered, not even the question of 1 million questions. So, but we are lucky in the sense we are only in a situation where we should do small perturbations. So at least if you know something good about it, our initial stage, and we can do something more a bit on the way with the belief. Actually, I already told you my view on this belief, but actually, just now Ivan showed us very interesting story. If you think about this belief, you are in a situation when your Poisson ratio is 0.5, you try to do small perturbation in the contact problem, and you are in a huge difference because you need to solve the problem from the very beginning, creating another problem G epsilon. Okay, so what I want now to do is to tell that if we have this initial information and we know something about this matrix a bit more than simply that this is a perturbation, but it's real perturbation of that kind, so we have something what we know absolutely everything about the function. So it's matrix function f, just to be nicely, because you would say something more because of this, goes to 1 at infinity, factorizable, of course, with a proper class. And what we are doing with that matrix, we're multiplying from the left and from the right with some other matrix function depending on the parameter phi. And this function has particular property, namely that at 0 point is 0. At 0 point is 1. And you'll see and all the problem what I will show you, physical problem actually comes to this, to that type of transformation. So what type of the problem? So if you can consider the problem when crack moved with a straight front and then front behind a bit deviates, this problem really considered like that actually was very difficult problem to solve. Was the most difficult problem I have ever probably done in my life with Andrea and Sasha. So the other problem, it's the problem of absolutely the same types, and if you, what Pavlos showed us today, that you have also perturbation due to the movement, and you have some shift in different part of the solution, you again comes to this story. Then you have situation when you have mixed boundary value problem with more than one point of separation of the boundary condition. Then you exactly come into that situation, and finally you have diffraction and scattering when you have this story, this typical fellow, because of other reason. You have this reason because of the type of the problem you're solving. Actually, there is something mixture between these two, and I put something like this, that those more dangerous if you think about the mixture of these two, because if you try to manipulate with this phi, thinking that phi goes to 0, those two problems are perfect because you're really going with a regular factorization. But those are not really always, because if you lose few of your separation interval, you lose a lot of physics inside this interval. You do never know what happens as a result of the limiting problem. Okay, so all the problem what was shown, what I was proud to participate in solving with Leonid's with techniques, so it was already showed many times here, and the most important story is that everywhere the scalar factorization came to the game, and this was because all the movement of the crack considered to be really pure steady state, that everything is preserved. But if would be any mismatches as Pavel shows today, it would not be so easy and so nice to do, and then we immediately comes to matrix factorization. And the main message now is that a lot of us, not all of us, but you know the activity to create metamaterials. If metamaterial start to destroy, it would not be steady state jumping from point to point. It would be very complicated movement from cell to cell, and then it's definitely matrix problem, and then no way to have even think about any scalar factorization problem in this particular case. So I would like to support what Michael Marder mentioned, that it's impossible to solve only analytically, because if you start doing things analytically, you even checking everything what you are checking, but I don't want to be deep inside the techniques, especially if I mention about crack movement. You should verify this by numerics, because you can find something in theory, and this theory even satisfying the admissible condition may not be achieved in real life, and vice versa. You would find something was analytically telling you this admissible impossible, but this admissible impossible would only mean that you have actually more complex movement, periodic movement, when the crack jumps with the different times from place to place, and then in those times would be everything absolutely perfectly admissible. So no problem with this. So only altogether is if someone wants to have the new results. So now I'm coming to one also very important point when we're speaking about this matrix factorization, especially with remembering that we have this parameter epsilon. This parameter may be something given, like if you have diffraction, scattering, and so on, and maybe something what you have no idea what is this, so you do not know the value of this parameter, like a cohesive crack where you don't know the length of this crack, or you have some other parameters what is also dependent on the solution itself. So we are not only solving the Wiener-Hoff problem, we're usually, or time to time, we're solving really nonlinear in that sense problem, because the parameter actually depends on the solution. And then you need to factorize many times, trying to grab from your solution this parameter, so it should be fast enough to compute in your iterative scheme all this factorization all the time changing. So this strategy to compute this factorization should be good enough. Okay, so I think everything is clear here, that we are in a situation. I look at the clock. I will be on time. So we need to construct something what would be effective, what would be probably not too much sensitive to the value of this parameter because we don't know the parameter. And is it possible? So for this particular matrix I showed you, probably our answer is very close to yes, but it's not finished. So we did something with Sergey. Sergey also mentioned about these 3 papers. So we started with the canonical factorization, then we came to the factorization with the stable partial indices, and then we considered general case with unstable partial indices, and then the result was, okay, probably I will skip a bit of technicality. So it's very easy. The idea is so simple that I understood. We discussed again with Michael Marder that he used the same idea when he factorized something 2 by 2 with his PhD students. So the idea how to construct this factorization is really very easy. So the message to take in case of canonical factorization work perfectly. Okay, it's not approximations. It's not asymptotic approximation. Actually, this is converged series, no problem whatsoever. In case of the stable set of partial indices, you have always you can construct your approximation, but you have now something like something is fixed by conditions that should be satisfied, and you always have 2 sets of constant which actually define behavior of your matrix function at every step of approximation, what you can choose for free, but whatever you are doing, you cannot preserve the fact that factors would go to unit at infinity. No way. And in case of unstable, you should have some additional, conditions which are constructive. You can check them, but you do not know in general case whether they always will satisfy or not. So this is my final slide with the open question. So if someone would really try to check the belief statement that everything is okay, but we already have 2 examples today that not everything is okay with the partial indices in terms of how they appear, not appear in the practical problems. So the second open question is, okay, my matrix G phi or G epsilon was not good enough we couldn't satisfy these conditions what we actually established, but we can a bit manipulate it with this function and then again find another path which will be close enough to the previous one, so we're happy again as a mathematician we can do something about this. So we have I don't have actually to explain what is a magic limit, because when you go with the speed goes to 0 in this movement lattice problem, the energy release rate is continuous, apart of the fact that in this point it's had no at all any derivative, and there are 2 formulas, magic formula simply written for some mathematician to come and to prove that they are the same, and they're coming from green functions of the problem which is stationary and green function of the problem which is for the moving crack. So the micro vibration, I don't want to speak, and the last, it's not open, yes, it's still open questions, what to do with a series of workshops, Wiener Hof workshops. We started some years ago in Aberystwyth, and this continues to Avera, then on conference in Padova. It's actually the Jury Necron, this workshop is in INI, but I think we already spoke to Nastya, probably she will be happy enough to take over this for the future, but she told me no way next year. So thank you very much for your attention.
You showed in brown, there is no. Is it a theorem or there is no idea how to do this?
Of course, there's no idea. This is a million dollar question.
Okay, and second, on two. You know, as I see, you and other maybe consider matrix as they are, without connection with the physical formulation.
Leonid,
maybe if you consider, you know, what physical formulation, what the details of physical formulation lead to a bad matrix, you could find a way regularization or something like that.
On a
So
fifth.
I mean to start in general.
Okay, Leonid, I mentioned on the fifth, I think, minutes of my talk that if the belief can be formulated in the form of theorem, again, I will repeat this. Any wise, experienced, and lucky researcher would always have canonical factorization. I believe in this statement. So I already made more accurate other theorem, what is more strong than what was written here. But again, this also should be proven. And this is even more difficult to prove because you should find wise, lucky, experienced researcher who would like to do this. So
Okay, any other questions?
Maybe not a question, but a short remark. Since I'm voting for optimistic point of view, I suppose that we know not too much about matrix. That is why probably something bad things happen. And what I would like to say more as a joke. The net of our constructive methods, it is now have two big holes, and many things put out of our intention to see what's happened in reality. Two big holes in our net. In this respect, today I found one joke. Maybe I read this joke first. Which language first? Russian or English? Maybe Russian, it is better.
We start with English.
We start with English. Start with English. Children coming to the house, crying to their father. Father, no net and no download it. And in Russian. Прибежали в избу дети, в торопях зовут отца. Тятя, нету сети и не загружается.
Okay.
So the conclusion is maybe we in further our steps we can make our holes quite smaller, and we can find some fish into this net.
No, if it's not a black hole, that it's okay. Then if it's black hole, would be difficult. Nastya, you probably would like to tell something at the end, because this workshop actually came to the end.
Special poesy devoted to matrix.
Sorry?
A poem
Poem
devoted to
the
matrix problem.
matrix.
The first I hear.
Yeah.
Yeah.
I mean, a comment to your talk. If we perturb a physical problem in a physically meaningful way, we're going to get a physically meaningful perturbation of the matrix, right? And that's something to be explored, and I think we're going to have a study group. So next week, I've sent you all emails, and in case you haven't yet or not intending to read the emails, I'll repeat basically what's going in that email. Next week, we're going to have study groups. So there will be 4 study groups on 4 different topics. You're free to choose any of those study groups, turn up, and we're going to discuss loads of interesting topics, including partial indices and stability and how we perturb things, and another one that about exact factorization, which Ilya has proposed, one on approximate factorizations and triangular matrix functions, non-factorable diagonal entries, and the 4th one is linked with the unified transform method and the Wiener Hof. So if you have any other groups you want to initiate, then please let us know and we'll email everyone out. But anyway, of course, we're halfway through, and most of the talks are over, but most of the work hasn't yet started. So I hope that the next 2 weeks is going to be the very productive weeks, which are going to hinge on what we've done in the last 2 weeks. Just a little comment, I'm not sure I said anything about the logo. So the logo, when I was creating, I wanted to emphasize that there are 3 aspects. There is the theory, there's the numerics, and there's the applications. And I hope that we all agree that all of those 3 things are very important, and if we combine them in the right way, then A, they look pretty, and B, they're very useful. On the social program, next week we're going to have a pizza night on Tuesday, and there will be wine and there might be beer, depending on who orders the stuff. And we're going to have a punting trip, I hope, if weather permits. But otherwise, we're all there to make our own contacts and collaborations and make the most out of the brilliant environment that we are in at the Newton Institute. So I would like to thank everyone for their time, their patience, and presentations and talks and being here. And I hope that we are going to have very productive next 2 weeks. And for those of you that are only here for this week, thank you very much, and obviously keep in touch with the rest of us. Okay.
Yes, and you're allowed to come to our cultural events, flying from continent or even from other places to stay in touch with us, not only on those events, but also scientifically, having been presented in a discussion, at least with your emails and suggestions, or if you really would like to do so, I'm sure that Newton Institute has enough facilities to have even video conference, so it would be not a problem at all.
Yeah, there's a room where we can set up Skype conversations. If any one of you wants to have a Skype meeting with someone else, there's a room for that.
Okay.